Hello and welcome to a presentation by ICDD's Executive Director Tom Blanton, Database-Driven Materials Characterization and Discovery Using Powder Diffraction File Databases. Presented at the Conference and School for Young Scientists, High Temperature X-ray Diffraction and X-ray Diffraction of Nanomaterials, HTXRD4.
Hello everyone, this is Tom Blanton at the International Center for Diffraction Data, coming to you virtually from Philadelphia, Pennsylvania, USA. Today's presentation will focus on using the powder diffraction file for materials characterization. While putting this presentation together, I was reminded of a visit I made to St. Petersburg in 2011. That's me right there. And it was absolutely wonderful visit, a great chance to meet some great people and visit a great city. And I hope to be able to do so in the future. Founded as part of ASTM in 1941, the organization became independent and took on the name JCPDS in 1969. Changed the name to ICDD in 1978 to reflect the more international nature of the organization. Materials Data Software Group joined ICDD in 2018. We have 40 full-time employees, 11 external editors, 321 members, a board of directors elected from the membership, with the MDI group located in Livermore near San Francisco, California, and the database ICDD group located in Newtown Square near Philadelphia, Pennsylvania, USA. Powder diffraction got its start 1916 and 1917 to Buy and Share in Europe, Hall in the US. And what they were able to show was that you could either take single crystals and grind them up, or materials that did not look like single crystals but still had microcrystalline nature, collect diffraction patterns, and see the powder rings, which we refer to as Debye rings. Hall went a step further and showed that you could use XRD for phase identification, where he took a mixture of two different sodium fluoride type phases, and when he analyzed that mixture, was able to show that you could differentiate the two different phases in the mixture phase itself. The powder diffraction file got its start really with a paper in 1938 by Hanawalt, Wren, Fravel. In Industrial and Engineering Chemistry, they published approximately 1,000 powder diffraction patterns based on materials that they had been analyzing at the Dow Chemical Company. And this is the original search manual that they came up with, because not only was it that they published these powder diffraction patterns, but they also showed a method of doing the phase identification. And the original Hanawalt manual, as it's shown here, it is located at ICDD in Philadelphia. In 1941, the first powder diffraction file cards were published. These cards were in fact on index size cards, written by hand. Number 1 is a bismuth organometallic. It had a simple list of D spacings, relative intensities, handwritten, and this one with the H in the corner means it was written by Don Hanawalt himself. The powder diffraction file, of course, has progressed over the years. It started with the cards. Books were published in 1950, magnetic tape, 1967. The powder diffraction file was the very first crystallographic database that was digital. In 68, it was microfiche. 71, hard disk. 87, again, an innovation. ICDD published the powder diffraction file at that time on CD, and as time went on, was moved over to DVD. 2008, we actually had a cloud server version of the database. It was the ICDD web product. 2016, product was distributed by USB, and coming soon, ICDD databases will be downloaded from the cloud. The database released in September, the 2021 release, We have our principal databases of PDF4 Plus, PDF4 Minerals, PDF4 Organics, and PDF2 database. And they all have different applications depending upon if you want to do quantitative analysis or mostly qualitative analysis. These databases are sold in 131 countries. And the key, particularly with PDF4 Plus, is the number of atomic coordinates available in entries with the 444,000 entries total. 336,000 of those entries have atomic coordinates that can be used for Rietveld refinement and quantitative analysis. The PDF4 Plus database itself, we have ICDD data as part of the database. We also have the Phys database as part of PDF4 Plus. We have NIST data, and we have the Linus Pauling file. All of these databases comprise PDF4 Plus. So you have the most complete database for powder diffraction ID. In May of this year, we announced a new partnership between ICDD and the Cambridge Crystallographic Data Center. We are again publishing CSD data in our organics database. And in this case now, the organics database has a significant number, over 400,000 CSD entries there. We're now adding the atomic coordinates to many of those entries. We have our ICDD data, a little bit of NIST data, as well as some ICSD data. So for anyone doing organic materials, particularly pharmaceuticals, the PDF4 Organics database would be the appropriate one to use for your materials characterization. Now, I mentioned earlier that we had the old Hanawalt manual, and now we have what we would call our electronic search form, which has many, many options in terms of being able to do data mining. We have different subfiles that you can search. Of course, the periodic table. We can search for patterns that have raw data in them, atomic coordinates. An important part, as I mentioned earlier, the different databases we have available. That's part of PDF4 Plus. But a very important part that makes ICDD unique when it comes to powder diffraction databases are quality marks. Every PDF entry goes through an editorial review process. And what that means is that every entry is reviewed for its quality, and then a quality mark is assigned so that you, the user, can determine how comfortable are you and how confident that the data collected by someone else is in fact good data. Example, why do you need editorial review? Here is a paper that someone published a claim that this was the diffraction pattern of sodium alginate. And right away it was suspicious because of these very sharp peaks present. Why would we say that? I myself have been doing some studies on alginates that we have now put in the powder diffraction file. And this is the diffraction pattern that one would expect to see for sodium alginate. Now you can see a little bit of some of the broad background in the published reference article, but it definitely, these sharp peaks say something else happened to the material. If you do phase ID using the powder diffraction file, you can easily identify that the crystalline phase in this sample is sodium sulfate. So where does sodium sulfate come from? As you read through the paper, the sodium alginate was washed with sulfuric acid. Sulfuric acid reacted with some of the sodium, and it made the sodium sulfate. And the result is that when the paper claimed this was sodium alginate, it actually is not. And that's what editorial review will do for you to try and eliminate these kinds of mistakes. Now, if I look at a powder diffraction file entry, some people still refer to the electronic entries as cards. Here's an example for an alloy, a bismuth iron scandium alloy. And you get the traditional despacings and intensities as you did in the old card. You can get HKLs if you know the unit cell. But what is now different is you can also see the two thetas, and you can get a simulated plot and adjust those two thetas because you can select which wavelength you happen to be working with to compare to the data that you're looking at. And you have atomic coordinates. can simulate patterns, and in many cases, we're putting raw diffraction data so you can compare your pattern to something that someone else has published. Beyond just being able to do the phase ID, there are also now a number of additional capabilities. It includes doing a visual of 3D pattern, basically the crystal structure. You can see the bonding. You get a simulated profile from all diffraction entries. Many of the entries now have the raw data included. You can also simulate selected area electron diffraction patterns, the backscatter Kikuchi patterns, and if you're using a 2D detector, you can simulate ring patterns for looking at multiple kinds of diffraction data. So the flexibility is there that allows you to do more materials design and materials characterization. So you can work with multiple radiation sources, X-rays of multiple wavelengths. You can input a specific wavelength if you're working with synchrotron radiation. We can also simulate constant wavelength neutron patterns as well as time of flight neutron patterns. So multiple ways to do comparisons, as well as the earlier mentioned selected area electron diffraction patterns to compare your data to entries in the powder diffraction file. I mentioned earlier about putting raw data in the diffraction pattern or into the diffraction entry, and this is an example of a halloysite 10A clay. And you'll notice that we have the traditional stick figures that people have used to say, yes, this is a phase that is matched. But now putting the raw data, particularly for something that's a disordered material like a clay, you can actually see what the disorder is. And so if you've run this particular clay sample, the peak positions will certainly be helpful to identify it, but to understand the whole pattern, being able to see the raw data is a big plus for materials characterization. So some of the kinds of materials we put the raw data in for very unique characterization capability, I mentioned clays. We also have a lot of polymer patterns now in the database. Here's Nafion polymer used for fuel cells. You can see the low angle, long range order, as well as the short range order in the polymer. We're putting nano patterns into the database so people can understand what the broad diffraction peaks will look like. And materials like graphite oxide that have some kind of layering structure. Again, all of these to help with the materials characterization of many, many different kinds of materials. Ultimately, you look at things to say, can I do identification? And here's a rock specimen from Australia. And if diffraction data are collected in 3 different areas, can we identify the components of this rock? Using the powder diffraction file, yes, the white crystalline material was identified as gypsum. We have the area here that contained both goethite, iron oxide hydroxide, and quartz. And the area right here is opal. And we have opal patterns in the powder diffraction file. So you can overlay the raw data with the reference pattern in the powder diffraction file and confirm, in fact, you have an opal containing material. In addition to being able to talk about diffraction data, we also include additional information like property sheets. Here's a case on a particular phase of the graphite oxide. We have a property sheet, and this particular property sheet is showing what is the effect of humidity on the OOL basal plane spacing. And we can see that as the humidity increases, the basal plane spacing increases, and as humidity decreases again, you'll see that basal plane decrease, telling us that you're getting intercalation of water in the graphite oxide. So it's additional information that the analyst can see when they're characterizing their materials. Additional type of property sheets, here's a europium gadolinium cobalt oxide sample. This particular sheet is including linear thermal expansion coefficient information. So if you're studying these materials, you're looking at thermal studies, you can in fact have a reference information sheet that tells you about expansion as a function of temperature. Additional capabilities in the powder diffraction file include composition graphs, ternary diagrams. This case happened to be an iron, cobalt, nickel alloy, and we can see all of these dots represent different entries in the database for different compositions. If you click on one of those dots, a PDF entry will open up. You'll get the information, including what's the composition, lattice constants. If atomic coordinates are present, then you can get that information as well as the 3D structure. So it's another way to find out what has been done, what's in the literature, what information can you grasp from crystalline structures of ternary compounds. We are including topology data in the database, particularly useful for porous materials, working with Vlad Blatov, Samara State University in Russia here, and using his program Topaz Pro. So this is additional information, and it's also very useful for ICDD from an editorial point of view to help determine the correctness of crystal structures. We have the capability of doing phase identification using microbeam analysis. In this case, you can enter in data from either an X-ray fluorescence or microprobe fluorescence analysis, put the elemental data in or put the oxide data in, and then do a phase search. And you can say, here's what my sample looked like. Are there any phases in the database that give a similar elemental composition? And you get probability factors with goodness of match between your data and the data that was published based on compositions of phases in the powder diffraction file. Another feature that we've added this year is using two-dimensional detector data. Traditionally, you would collect a data set, and if you want to get the full diffraction pattern, what you would do is you would actually collect multiple frames, and as you collect each frame, you'll get a different amount of the diffraction spectrum. What would historically be done with data like this is to read it all in and convert it all to a 1D diffraction pattern to try to do your phase identification. We now have the capability of actually reading the 2D data, working with that data, and being able to do the phase ID and do a 2D pattern overlap of the different phases, identify the phases, and do a semi-quantitative analysis of the phases using our I over I corundum RIR capability built in the powder diffraction file. So it's another feature, another capability added for the analyst to use to do a better job of materials characterization. This is a meeting about high temperature work, which means non-ambient capabilities, and the powder diffraction file can help in this area as well. There are over 54,000 non-ambient entries in the powder diffraction file. They can be non-ambient temperature, non-ambient pressure, or both. Here's an example of a in situ high temperature X-ray diffraction experiment I was involved with a few years ago, looking at silver sulfide. And the interest was that as you heat the material up, it becomes a nice conductive species, and trying to understand what's going on. You look at the high temperature data, and in fact, we can see the known structure of monoclinic at room temperature. When you heat it up, it converts to a body center cubic phase. But notice you have what appears to be an amorphous component. And what this really is that the silver in the silver sulfate now can migrate throughout the lattice. So you have this disorder component, but it's the silver migration that makes the phase conductive. Heat it up even further, and at 650 C converts to a face center cubic phase. And again, you have disorder because the silver can in fact migrate throughout the lattice. So we can take that data and put the raw data in the diffraction file so that not only do you get a list of peaks from despacings and intensities and the HKLs because we know the unit cell, but you also can see that raw data and understand that when you're looking at it yourself, It's due to the fact that you have the silver ion migration in this phase. We've put together a technical bulletin about thermal expansion because you can use the powder diffraction file with multiple entries from different scientists to help do more thermal expansion capabilities when it comes to doing materials characterization. An example is a PDF search for tetragonal zirconium oxide phases. And when you do that, you have a number of hits here. Upon looking at one of the entries, you'll find that you have entry here that's tetragonal, and it has an icon here that's lit up called temperature series. When you click on that, it will ask you, do you want to focus on similar materials with the space group P4 sub 2 over NMC? And when you do that, you'll have a list of entries here that you can do your characterization on. When you look at these simulated patterns, you can in fact see as a function of temperature, there is a shift in the diffraction peaks consistent with thermal expansion. When you look at the cell volume as a function of temperature, we actually found two populations. One population that occurred at room temperature and one that occurred at varying temperature. This, it turns out, is non-ambient, but it's non-ambient pressure. This is your non-ambient temperature data, and so this is what we focused on for thermal expansion. If you look at the data here, plotted out, you can fit a curve to that. You have the option of looking at linear, quadratic related curves. This is nominally linear, and you can pull out the thermal expansion of the zirconium oxide tetragonal phase based on this data. But you can also look at the A and C lattice constants, and we see that at high temperature, they're nonlinear. The A lattice constant starts to drop off in terms of expansion, but the C lattice constant starts to increase. The net result then was what we saw, that a nominally linear volume expansion, but A and C is anisotropic. So this is another feature of the powder diffraction file, because we have so many entries of different thermal data for particular phases. You can extract for many of these phases the expansion coefficient information. We have other categories that you can search beyond just, for example, elemental search. You can look at formula, classifications, crystallography, etc., to do data mining with the database. One of them of interest is classifications. And if I look at that, we have mineral, zeolite, organic functional group. You can also search on Pearson symbol, prototype, formula type. So if you're working with the material and you say, well, I have a prototype, what phases could that match in the powder diffraction file? If I expand upon mineral classifications, I can say I'm interested in a particular mineral group, amphiboles, and I can even go to groups and subgroups, such as the 2-octahedral group here. Click on that, do your search, and you can get the number of entries in the database. Any of these entries show up on your search, simply double-click on one of the entries, and the PDF entry card itself will open up, and you have all the information that you're looking for in terms of your phase identification, clarification, atomic coordinates being available. You can investigate the 3D structure and see, in fact, how the atoms are arranged in that particular unit cell. So classification, as well as prototype studies, another way to help do materials characterization. Some of the features that we offer on our website, ICDD.com, we have available for free download the DICVOL 14 indexing program from Daniel Aware. We added a graphics interface to it, so it's easier to pick out your diffraction peaks. We have a pattern converter where you can, in fact, import your data and get a pattern visualization to see what it looks like, convert it into an ASCII file format that can then be used in multiple diffraction analysis programs. The other thing we've added is a PDF phase search available at ICDD.com. In this case, you can enter in information. This example is barium niobium oxide, and what you will get is information telling you, are those phases in the database? So you'll get some kind of output, tells you the phases that are available in the database and which database product it's available in. Now, it won't give you the PDF entry, but it will at least tell you if we have that phase and what database you could find that phase in. I'd like to just point out that ICDD does have a grant and aid program. Each year, ICDD extends financial support to qualified investigators who are working in materials study and generating new novel X-ray powder diffraction data. We also have been accepting more recently neutron diffraction data. In the past 10 years, we've issued 344 grants. This past year, 37 grants in 12 countries, and providing over $330,000 US in financial support for materials research this past year. Now, I bring this up because an opportunity exists for work that's going on in your laboratory. You can see the countries that have submitted proposals, including Russia. And what we would like to be able to do is have more participants in this program. So if you think you might be interested in the grant and aid program, where you collect diffraction patterns on new materials and would like to get some financial support, we would ask that you contact Denise Delcasal at delcasal@icdd.com. She can then give you the information you need for, if you're new to the program, how to get started, and also an opportunity to understand once one becomes very well established in the program. We've had very good luck in terms of getting a lot of data into the powder diffraction file from the grant and aid program. If you have questions about the program, I would also recommend that you contact your regional co-chair, Evgeny Antipov. Evgeny is a well-respected member of ICDD. He's a McMurdy Award winner. He's an ICDD Distinguished Fellow, and he also is an ICD Distinguished Grantee. So if you have questions about participating with ICDD or the ICDD grant program, Evgeny can help you with additional information. And I'd just like to point out that I had the privilege of giving Evgeny his Distinguished Grantee Award. And as you can see, this was me, this was Evgeny, and this was many, many years ago when we were just a little bit younger than we are today. So with that, I'd like to say on behalf of the ICDD group, those in Newtown Square, Pennsylvania, those in Livermore, California, thank you very much for the opportunity to speak to you today. This group, these are the individuals that make everything happen. And what we feel is that we have the powder diffraction file, which is the best powder diffraction database in the world. But it's not just a powder database, it's a materials characterization database. So with that, I'll say thank you on behalf of ICDD. I appreciate the opportunity from the organization to let me give this presentation, and I hope those of you that are attending this meeting have a successful and enjoyable conference. Thank you, and good day.
Don't forget to like and follow ICDD on Twitter, Instagram, LinkedIn, and Facebook. More information on icdd.com. Contact us at info@icdd.com.